Welcome to This Explainer. Today, we're taking the abstract world of math and literally turning it into a game. We're going to unpack a super fascinating chapter from our source material that reveals the foundational secrets of numbers. If you've ever felt like numbers are just, boring symbols on a page, prepare to see them as living, breathing patterns. We're starting with a simple playground game and leveling all the way up to prime factorization.
Here's our game plan for today's explainer, taking us level by level through this chapter's essential building blocks. We're kicking things off with the Idli-Vada number game, then moving on to prime and composite numbers, unlocking the sieve of Eratosthenes, exploring coprime numbers, and finally, wielding the prime factorization tool. Let's get into it.
Section 1, the Idli-Vada number game, where we play with multiples. Picture a bunch of kids sitting in a circle playing a counting game. One child says 1, the next says 2, and so on. Pretty simple, right? But there's the catch. When it's the turn of 3, or literally any multiple of 3, that player has to say the word idli instead of the number. And when it's the turn of 5, or any multiple of 5, they have to say vada. It creates this rhythm, a mathematical pulse happening right there in the circle. If you mess up, you're out. But the real trick, the exact moment where the game gets totally chaotic and fun, is figuring out when you have to shout both snacks at the same time. So when exactly do you say Idli-Vada? Let's break down the rules here. We're essentially tracking two completely different rhythmic patterns. For the Idli pattern, we count by threes, 3, 6, 9, 12. For the Vada pattern, we count by fives, 5, 10, 15, 20. We are actively waiting for the very first time these two mathematical patterns collide. When a number is a multiple of both 3 and 5, you've got to shout Idli-Vada. Boom, there it is, 15. 15 is our absolute first common multiple of 3 and 5. It's that magic moment in the circle where the patterns sync up. Honestly, understanding this simple collision of multiples sets the stage for everything else we're going to look at today. All right, now that we've found our common multiples, let's meet the main characters. Section 2, prime and composite numbers, the ultimate building blocks. Prime numbers are basically the unbreakable atoms of math. The source chapter highlights that mathematicians have literally been obsessed with these since ancient Greek times. A prime number has only two factors, 1 and the number itself. Think of 2, 3, 5, 7, and 11. You simply cannot break them down into smaller whole number factors. They are the fundamental ingredients of everything else. Then you've got your composite numbers. These are the guys that do have more than two factors, like 4, 6, 8, 9, and 10. Because they have more than two factors, they can be dismantled. You can break them apart into smaller pieces, because they're literally composed of those prime building blocks we just talked about. But wait, what about the number 1? Well, 1 is a total lone wolf. It's neither prime nor composite. Why? Well, it only has one factor, itself. It doesn't fit the definition of a prime, which strictly requires exactly two factors. And it certainly isn't composite. It just completely stands alone as its own thing. Which brings us to Section 3, the sieve of Eratosthenes, or how to find primes easily. Our source chapter introduces this absolute cheat code left for us by a Greek mathematician named Eratosthenes around 2,200 years ago. He developed this step-by-step algorithm to just filter out composite numbers. First, you cross out 1, then you circle 2, our first prime, and cross out every multiple of 2 because they're all composite. Then circle the next uncrossed number, which is 3, and cross out its multiples. You just keep doing this. Eventually, all the composite numbers fall through the sieve, and only the prime numbers remain. It is so incredibly satisfying to do. Okay, moving to Section 4, exploring coprime numbers and their independent makeup. So what are coprime numbers? Basically, if you break two numbers down to their mathematical DNA, they're prime factors, and they share absolutely no common prime ingredients, they earn the special title of being coprime to each other. They are completely independent in their makeup. It's like they're from two entirely different mathematical families. And finally, Section 5, the prime factorization tool, finding the exact recipe. Prime factorization is the ultimate tool we use to check for all of this. Every single number greater than 1 can be written as a unique product of prime numbers. Take 84, for example. If we break 84 down into its absolute smallest prime ingredients, we get 2 times 2 times 3 times 7. There is literally only one way to factorize a number into primes like this. It's exactly like finding the unique recipe for the number 84. Let's put this tool to work and test out two numbers, 56 and 63. If we put their prime factorizations side by side, we can compare their DNA. For 56, we've got 2 times 2 times 2 times 7. For 63, it's 3 times 3 times 7. We can immediately spot a shared ingredient here, the number 7. Because they share prime factor, the text shows us this proves they are definitely not coprime. But now let's see how this looks with a totally different pair, 40 and 231. The prime factors of 40 are 2, 2, 2, and 5. The prime factors of 231 are 3, 7, and 11. Are there any common primes here? None at all. Their prime factors are completely different. This brilliantly illustrates a true coprime relationship. Even though both 40 and 231 are composite numbers themselves, relative to each other, they're perfectly coprime. To wrap up this explainer, let's bring it all full circle and revisit our starting game with a massive challenge from the chapter. Imagine the kids in the circle kept counting and counting. What if the Idli Vada game was played all the way up to 900? Well, because we understand multiples now, we know that every 15th number is an Idli Vada. So by the time they hit 900, those kids would end up yelling Idli Vada exactly 60 times. We've moved from shouting snacks in a circle to uncovering the hidden, unbreakable structures that govern all of mathematics. So I'll leave you with this. Armed with the sieve of Eratosthenes and the tool of prime factorization, what other hidden mathematical patterns are just waiting in the numbers around you right now?